Welcome back. So let's recapitulate. So you have started defining your problem space, essentially, right? And Megan has already talked about this earlier. So in your project, you have essentially asked, or in our project, we have asked why this illusion occurs, why the train illusion occurs, and whether it could be explained by unreliable vestibular signals. Now, we could have asked many different questions. For example, in which situation this phenomenon occurs, which, going back to yesterday's lesson, would have been a descriptive or what question. Or we could have asked about the neuronal mechanisms leading to this illusion, which would have been a how question probably. And for each of those different questions, you could formulate many different hypotheses. For example, for the descriptive question, we could hypothesize that it's window size or speed or weather conditions that matter. And each of those hypotheses would be potentially meaningful for a series of different goals, right? So for example, examining window size could be interesting in the quest to reduce nausea, for example. Or maybe we're interested in window design or what processing characteristics in visual cortex lead to this illusion. Now, those are all reasonable questions, hypotheses, and goals, right? But every one path taken, every combination of these would lead to a very different model. And so therefore, precisely defining your problem space really defines and constrains the actual modeling project and helps ensure success. So it is therefore crucial to specify the problem space because it represents the knowledge gap that we want to fill. So that's the thing we do not understand yet and that we would like our model to shine light on. Okay, so with that in mind, typically what we would do now is essentially do some literature review, right? So we have some initial ideas about the phenomenon. We have learned a little bit about it, but now we would go out and essentially ask, well, what has already been done? What kind of models exist, etc., etc. Now, for the sake of time, we will not do this here, but you will do this for your project essentially later on. Okay, so once we've done that, right? And as also okay, so we have earlier introduced some pieces of background information about the train illusion. Now for you, oh boy. Now the importance of doing the background research, the importance of reading is really that it allows you to ask good questions, right? So, and in order to ask good questions, you essentially need to know the details of the phenomenon. You need to learn about the phenomenon. You need to know what's known or unknown regarding the mechanisms at play, whether there are potentially similar situations and experiments that have already been studied, right? So in summary, good scholarship, essentially as usual, leads to good science and good modeling. Okay, so once you have your questions and goal, right, and you have done the literature review, we're now ready to essentially think about what the model might need, which ingredients. So what are the ingredients of our model? To essentially identify the ingredients, we want to ask what variables are needed in the model. What ideas, what mechanisms, what operations, what concepts are essential? What kind of data would we be looking at? Do we have any idea of the potential inner workings that we might think about in terms of the model? So to illustrate how this step might work, have a look at how our group approaches this for the train illusion and learn from their mistakes. And then after that, it's again your turn to think about the ingredients needed for your modeling project. Okay, welcome back, group. Remind me of your question again.
All right, so we have our specified question from last time. How do noisy visual and vestibular estimates of motion combine to lead to illusory percepts of self-motion?
Okay.
It feels like we can start writing the model, right?
Oh,
Marius,
really?
you're good at Python.
Really? So what exactly are you going to use in the model?
Well, Python.
And noisy estimates of self-motion.
Deep learning?
Right. Okay, so maybe you should think about what a typical experiment would look like. What was manipulated and measured in the data that you have?
Okay, so people were put on a chair with the train window attached to it, and through that you could see another train. And then sometimes that train was moved and sometimes the chair was moved with the participant on it.
So in the experiment, then they were controlling what people see, and they were also controlling the vestibular input by moving the chair around. Am I missing anything? Was there anything else?
The movements were very slow and slow acceleration.
Okay, so not jerky,
Mm-hmm.
but it was always the same, right? Always the same movement in the chair?
Yeah. Oh, and then at the end, the participants had to say how fast they were moving and how fast the other train was moving.
Okay, that's great. So these are potential aspects that somehow need to go into your model, right? So which one of those should be actually part of your model?
Okay, so it should have a visual input and a vestibular input, and then you estimate your self motion. Do we need the estimates of the train motion too?
Yeah, I guess from the experimental data we have, it should definitely compare it to what the participants were perceiving.
So what do those percepts look like? Like what shape can the estimate of self-motion take?
Well, it kind of falls into two categories. Either you feel you're moving and the other train is not, it's stationary, or you feel like you're stationary and the other train is moving.
So there's essentially no middle ground, right? With like a little bit of illusion or something like that. So what kind of system would give you like an either or, like an extreme output?
Right. Well, in this data set, there was no middle ground. So they all had the correct percept, or it was kind of flipped. I can imagine there's other situations.
Yeah, but it seems like, at least for this, if we want to focus on this one, then it's either or. It's the sensory information is interpreted correctly, or it's not. It's either one way or the other. It's like a binary decision.
Okay, so that means we can't average the signals together. So that means we just have to have some cutoff and say like, now there's self-motion and now there's not.
Okay, so you essentially need some form of a threshold or criterion, right? And you essentially will need to try out some form of a mechanism in your model that implements a decision to come up with this binary percept.
Okay, so it seems like we have the visual input, like seeing the motion, and the vestibular input, feeling the motion in the chair. And we also have this decision criterion, this boundary where you feel like you're moving or you're not. And then we can get a self-motion estimate. Cool, we can start writing some Python.
Well, those are some very good ingredients for a model indeed. And I'm sure you will need them, but how are they actually connected? So how would you write a model if you don't know how they're connected?
What do you mean? Like we get an estimate of self-motion, velocity or speed from the vestibular and the visual inputs, right? So if the velocity estimate we get from both of these is low, then we say there's no self-motion. And when it is high, there is.
But wait, hold on. The visual input's always the same, but sometimes you feel like you're moving and sometimes you feel like you're not. So that would mean it has to be, I guess, the vestibular signal that is the one driving whether you feel like you're moving or not.
Well, yeah, but we check the data, right? It's so super noisy. You can almost see nothing in there.
Yeah, that's great. So how could you make the noisy vestibular signal more useful? Well, so what kinds of things would a system do to deal with super noisy signals?
To get rid of noise, you could average it across the whole thing, the whole trial. Or maybe we can use like a moving average filter or some to get rid of some of the noise at least.
Yeah, but remember, in the end, you need to turn this into a motion estimate, right?
Oh, yeah. I guess even if you smooth it out, you still get a noisy or smoother acceleration signal, because that's what the vestibular input is it's acceleration. But yeah, we need velocity, not acceleration. Maybe we could integrate it in addition to filtering.
Yeah, that sounds good. So if we integrate it, we just get velocity from acceleration.
Okay, so do you have all your ingredients now?
Well, we got our inputs. That's the vestibulars. That's only the vestibular signals, because the visual inputs are the same anyway. They're not informative. And then we use the running average filter, and we integrate so that we get from the acceleration to velocity.
And then for the output, we need that binary decision mechanism, the threshold, to decide if we feel like we're moving or not.
Cool. So it looks like you have all your ingredients, and all you need to do now is formulate hypotheses in the next step.
With deep learning?
No.